So I thought we'd do a simple state machine just to walk through the whole process, get all the way from the definition of the problem to the bubble diagram to the truth tables to the Carnot maps and then to the circuit. So here's our problem. We have a security guard and he's sitting at a panel watching status lights, and these status lights indicate whether doors are open or closed in a building. It's after hours, so if a door opens, that's probably a bad thing. So we're going to have a switch assigned to each door, so when the door opens or closes, the switch changes its state. So what we're going to define is the switch is 0 if the door is closed. And then we're going to have the opposite condition, where if the door gets opened, then the switch is changed to the 1 state. Now the status panel needs to indicate that, so rather than just have the LED that indicates everything's okay, maybe change color or turn off, we're going to say that if the door's closed, all is well, and we're going to flash green. We'll have a green LED on the panel. And if the door is opened, we're going to flash red. Makes sense. Now, if this was a real condition, if a door opened, it was never supposed to be open, you'd probably have it flash red and just stay red, right? Maybe even sound an alarm. But we're going to keep it simple. So if the door is closed, we're going to flash green. If it's open, we're going to flash red. Now, this notion of flashing is kind of curious for state machine, isn't it? Because we're having this periodic clock being sent to our machine. Well, how do we get something to flash? How do we go from on to off and then back to on and then off and just do this in a periodic way when we have this periodic clock? Well, if you think about it, an obvious way to do that would be to define two states, say A and B, and as long as the switch doesn't change states, as long as it's either closed or open, we simply hop back and forth between the two states. And we simply make an assignment that if we're in state A, the LED is off, and if we're in state B, it's on. And you can see that for a periodic clock, we'll now just hop from off to on to off to on. We'll just do that continuously. In our bubble diagram, we have to have two arrows which constantly move us back and forth between these states. Remember that an arrow is a clock event. So an arrow means we make a transition from one state to another, and that can only happen on the action of a clock. What determines what state you go to is determined by the inputs and the current state of the machine. Right? So we need to define a machine that does that. So we need a pair of states to flash green and a pair to flash red. So let's put our A bubble and our B bubble here. We'll add another pair, C and D, so that when we want to flash red, we don't have any confusion. These two states are going to be associated with a green LED, so we need another pair. Alright, so if we assume A and B are associated with green, then when the switch is closed, we want to flash green. So that would mean when SW equals 0, we're just hopping back and forth. Right? And by symmetry, when the door opens, we have to flash red, so we would be hopping continuously back and forth between red as long as the switch is in the open state. Now obviously if the door is closed and we open it, we have to be able to move between and then shut again. We have to move in between these pairs of states. So there's a lot of ways to do that. You could say if I'm in either A or B and the door opens, I move to C. Or you could have it move to D, and so there's a lot of different ways you could move. We're just going to keep it nice and symmetric. I'm just going to say, if I'm in B and the door opens, switch is equal to 1, I go to D. And if I'm in A and the door opens, I move to C. There's all kinds of ways of defining the transition. I just picked that one. So this is sort of a dividing line, isn't it? Everything below this line has to do with the switch being 1, and everything above it has to do with the switch being 0. Well, if the door closes, I need to move from the red state back to the green state. In a real security scenario, once you got into this state, you probably wouldn't leave until the security guard did something specific, like resetting the system. But as I said, we're trying to keep it simple. So if the switch goes back to being closed, we need to make a transition back here to the A state, or the call the green state. Okay? Now, this is a nice symmetric problem. You can see the symmetry. There are 2 arrows that leave every state and 2 arrows that enter every state. So it would probably have a pretty complete system, and it's nice and symmetric. So our truth tables are probably going to end up being pretty simple as well. But this is the general procedure. Sort of use your intuition to figure out, okay, what kind of states do I need here? How many states do I need? Draw your bubble diagram, and then make sure that every possible input condition creates either a motion out of a state or stays in the state depending on the condition of the input, but make sure all those input conditions are taken account of. Now, normally at this point we would assign a bit pattern to A, B, C, and D and start writing our truth table. But let me just pause that process just for a minute, and let's just draw the table a little bit differently. We're just going to, it is after all a state transition table, so let's leave these labels in and write the state transition table that way. So on the left, you know, we have inputs. Okay, and some of those inputs include the present state. The present state of the system. And the combination of inputs and present states are going to create a logic input to memory cells. The memory cells are D flip-flops operated by a clock. The D input is going to be the output of this truth table. The Q output, true terminal, which is the output of the memory, that actually is going to be the present state of the system. The future state, we can call it future state or next state. That next state is really the input to this memory cell, because when the clock comes along, that input is copied to the output. So sometimes that's a point of confusion. The present state is the static output of the memory element. The next state is the input to the memory element. Well, having done this, now we can just write down every possible combination of present states and input states to get our state transition table done. Well, we only have one switch, so we know there's 4 possible states that we could be in with the switch closed, and there's 4 possible states we can be in with the switch open. And those states, I don't have to list them in any particular order, but why don't I just list them as A, B, C, D. A, B, C, D. Here's all the states we could be in. Here's all the switch states we could be in. So we've accounted for every possible condition that could, on the next clock, lead to a change of state. Or not. Sometimes the states don't change. Remember, if you have a bubble that has an arrow that feeds back into the bubble, it means for that input condition we stay in state X. We don't leave state X. We don't have that case here. Alright, so now it's just a matter of looking at your bubble diagram and figuring out the next state. So if our switch is closed, we should be flashing green, which means we're going to have to be in A or B. But if we're in A and we want it to flash, the next state has to be B. And if we're in B and we want it to flash, the next state has to be A. Okay? If the door is open, we should be flashing red. And so if we're in the C state, we've got to go to D. And if we're the D state, we've got to go to C. Now these 4 states, they're the ones that, the transitions. These are the conditions that lead us to a transition between A, B, and C, D. So if the door is closed and we're in C, then we go back to the green condition, which would be A. And if we're in D and the door is closed, we have to go back to B. Similarly, if we're in the flashing green state and this door opens, then we've got to go to C in the case of A and D in the case of B. So this is one way of writing the state transition table to avoid confusion. If you're at all confused by throwing a lot of 1s and 0s around, keep it abstract by using the state label and get this mapping correct in your own mind, and then you can go back and change the table, fill it in with the binary representation of the symbolic states, and then proceed to analyze the truth table. So now I'm looking at this now, it looks like we have done the correct mapping of the present state to the future state, and we've accounted for all states. Notice we have a lot of symmetry here. BAAB, CDDC. It could very well be that the state machine is going to be easy to design because of this symmetry. And also, of course, if you think about it, when we're flashing green or red, let's take the green state. If we're flashing green or red, then in only one of these states is the LED green on. In all other states, green would be off. Similarly, when we're flashing red, only one of these states, C or D, will have the red light on. In all other states, it'll be off. So it's probably also going to be true that when we decode the state into the LED control, it's going to be a very simple mapping because it can only happen if, say, you're in B or D. Okay. All right, so having done this, then we'll pause for a moment. We're going to take this table, we're going to convert it into a binary truth table, and then we're going to solve the Carnot maps to figure out what our logic should be to drive our memory elements.